linear function. So we looked at the graph of the parent linear function, just y equals x, yesterday. Can anybody just remind me what that looked like what the y-intercept was or what the slope was? Anybody remember? It went through the origin and had a slope of 1. Okay, so I am just going to put that on here as a dashed line for reference. This is where the linear parent function is. And I'm just going to label that y equals x. Okay. Now, what this is asking us to do in number 1 is to graph the function 2x plus 1. They say f of x equals 2x plus 1. Okay, and then write the domain and range. Okay, well, there's 2 ways you could do this graphing. You could create a table, like they've got a table here for us, or if you are understanding your slope-intercept form of linear equations, remember mx plus b form, that's slope-intercept form, because you can see your y-intercept. What part of that is the y-intercept? The m or the b? The b. So our y-intercept is what here? 1. Okay, that's your y-intercept. Okay, and m is the 2, and what does m represent? Slope. Okay, so if you have your equation in this form, you don't need a table of values. You can just start at your y-intercept at 1. So on the y, remember this is the y-axis, this is the x-axis. So I can start on my y-axis at 1, bless you, and then I can count my slope to get to the next point, to get to a second point. What do I mean when I say count my slope? Rise over run, exactly. If you need to make a little note of that, slope is rise over run. Okay, so from that intercept that I plotted, I'm going to rise 2, because my slope is 2. Now, if there is no denominator, it's an understood 1, right? So rise 2, run 1. OMG, stop with this. Okay, so rise 2, run 1 gets me here. Rise 2, run 1. Okay, you can go in the opposite direction. You can go down to left 1. Okay, and then I've got several points, and I'm going to draw my line through those points. If you are kind of picky on drawing your lines, if you really like straight lines, I do have rulers if you'd like to use them as a straight edge. They're in the supply drawers back here. One of those drawers is labeled rulers. You're welcome to borrow a ruler. Okay, so here's our line. I'm going to label it f of x, because that's what they called the function. They said this is f of x equals 2x plus 1. Okay, so that's a refresher on how to graph your line using the slope and the intercept. Now, that's not the only way I could have graphed this. Okay, in Desmos, I can write my one sec. I'm gonna get a Desmos window open real fast. Over here. So in Desmos, I could write my equation, and you can type f of x or you can type y. Y'all remember that f of x and y are interchangeable, right? F of x is the same thing as y. So it was 2x plus 1. So you can write your equation and look at the graph. You can click on the gear, and it gives you the option to create a table for this equation. So if you create a table, then you have a table of values of points that you can plot. Okay. Your table, when you do this method in Desmos, when you type your equation, click the gear, click the table, It's always going to give you the x values, -2 to +2. So if there's, sorry, I got hiccups all of a sudden. If there's another x value that you need, you can just type it in. If I want to know, okay, what about when x is 3? I can type a 3 and it's going to automatically fill in the y value. So you can make your table whatever x values you want, okay? So you can get a table in Desmos and then plot the points if you don't remember how to graph from slope-intercept form. Okay, so I'm going to go ahead and fill in that table that they gave us with those values that Desmos calculated for me. I did not have to go in and calculate those on my own, but I need to see what they were again because I already forgot. So let me split screen. Okay, so that's -3, -1, 1, 3, and 5. So I didn't need anything else besides x is -2 to +2. So I was good. It gave me all of those. If you would like to make a side note of where we got those values, of course you can. Remember, you're taking whatever is in the x column and you're plugging it in for x here. That's how we're calculating the y value. Okay, you don't have to do that by hand though. You can use Desmos. Okay, so you type the equation and then you click the gear and then you click the table. And that's how we got the filled in table. And then if you need to, you can type any X values that you want. Okay, so that's how we get the table in Desmos if you need to make note of that. All right, what's the domain and range of this graph? That gray line that I graphed, what's the domain and range? We talked yesterday about domain and range of the parent function. And we talked about how it goes on forever to the right and to the left. So what was the domain? -infinity to +infinity, right? This domain is our x's. That is going to be the case for every linear function. If you have a linear function, okay, you have a graphed line, you don't even have to have the graph to see that it goes on forever in both directions. If you have an equation that's a linear equation, you know the domain and range without seeing the graph. It is going to be all real numbers or -infinity to +infinity for all linear functions. Okay, the only time a line would not have that as the domain would be is if it was a vertical line. If it was straight up and down, but then it wouldn't be a function. So all linear functions have this domain and range. Now, question 2 starts to talk about inverse. So up here it says that an inverse function serves to undo other functions. That is, if f of x produces y, then putting y into the inverse of f will produce the output of x. That sounds super confusing to me, and I'm a math teacher, so I can imagine that it sounds pretty confusing to y'all as well. So I'm going to reword this. I'm going to put this in simpler terms, okay? For an inverse, we switch the input and the output, okay? So I'm going to put that here. The input and output switch. So input, that's your x's. Output, that's your y's. So essentially your x and your y just switch when you're getting an inverse function. Okay, so here in number 2, it says to graph the inverse of that function that we've graphed the original function. Now they want us to graph the inverse of it. Okay, well, to find the inverse, I'm going to switch all the inputs and outputs, all the X's and Y's. So what was the X column over here is going to become my Y column. I'm going to put all of those X values as my new Y values. And what was the Y column over here is going to now be my X column. My inputs are now my outputs and vice versa. So now that's -3, -1, 1, 3, and 5. So I literally just switched the X and the Y column to create the table for the inverse. So now to graph that, I'm going to plot these points. Okay, so this is the other way to graph. I don't have the equation of the inverse. I have the equation of the original, but I have the table of the inverse. So I'm going to just plot points. So I'm going to go to -3, -2, and plot a point. -1, -1, plot a point. 1, 0, 3, 1, and 5, 2. And then I'm going to draw a line through those points. That is the linear inverse of f of x. So the way that we indicate inverse with function notation or with any notation is a little -1 exponent or power. So instead of just f of x, I'm going to write this as f to the little -1 up there of x. And that is read f inverse of x. So this is the original function in gray. This is the inverse function in pink. Now, what do you notice about the relationship graphically between those two and that line y equals x that we put on there? They intersect on that line. They have the same spot, happens to be on that line. Good. What else? What would happen if I folded my graph, if this was paper, and y'all have it on paper, but if I folded this along that dashed line, what would happen with all the gray and pink points? They would all match up, right? It's a reflection across that line. This is a line of symmetry. Y'all see that? It's symmetric across that line of the linear parent function. That is always going to be the case for inverse functions. So I'm going to make a note under that graph. Okay, I'm going to say inverse functions are symmetric over the line y equals x with their original function. When I write FCN like that, that's my abbreviation for function. Okay, you can put this in your own words. I may not have worded that the best, but a function and its inverse are symmetric, okay, across that line y equals x. So a function and its inverse are a reflection, or they are symmetric across that line y equals x, as long as you understand that. What's the domain and range of this pink line? Yeah, it's the same. I told you when we wrote the domain and range over here for the original function, I said all linear functions will have that same domain and range. Okay, so it doesn't, the function is linear, so the inverse is linear, and so the domain and range of both is all real numbers. Okay, now we're going to talk about how you can find the inverse function from an equation without graphing. Okay, so if I don't have a table or a graph, okay, I don't have a list of ordered pairs, any of that stuff, I just have an equation. Okay, we're going to follow this 4-step process to get from an equation to its inverse, or from a function to its inverse. Okay, so with that same equation, f of x equals 2x plus 1, we are going to algebraically find the equation of that inverse that we just graphed. Okay, so step 1 says change function notation f of x to y. So I'm going to replace the f of x with a y. Step 2 says switch x and y. Okay, so up here we did the switching in our tables. We switched the x and y columns. We don't have tables now. We're in the equation. We are going to switch where x and y are. So this is now x equals 2y plus 1. And then step 3 is now solve for y. We want to isolate the y now because we want it in y equals again. So what am I going to do to now solve this equation for y? I want to get the y by itself. What do I move? The 1 first. Remember, when you're isolating a variable, you move any constants first. So -1, because that's the opposite operation. I cannot combine x and -1. Those are not like terms. So it stays x minus 1 equals 2y. Now, how do I get rid of that y? Okay, I'm going to divide. What you do to one side, you do to the other. Now, the other side has 2 terms, an x and a 1. Which one of them do I divide by 2? Just the x? Just the 1 or both? Both. What you do to one side, you do to the other side, the whole side, not just one term. So the entire side gets divided by 2. So some people like to leave it like that. X minus 1 over 2. They don't want to simplify it. Okay, I like to have my linear functions in slope-intercept form. Okay, so I'm just going to separate that. I'm going to say, okay, I'm doing x divided by 2, and I'm doing the -1 divided by 2. So you can separate it like this and individually divide them by 2. Okay, and that's the same thing. Now we've isolated our y, but we need a way to indicate that this is not the original y. This isn't just y. This is the inverse of y. So I'm going to use that little -1 exponent that I showed you a second ago. So that indicates this is the inverse of y. Y was 2x plus 1. The inverse of that is x over 2 minus 1/2. Okay, or another way you could write that, they do want us to put it, it says step 4 to put it back in function notation. Okay, so they want us not to write inverse of y. They want us to rewrite that in inverse notation. And instead of x over 2, what's understood to be in front of the x in the numerator? A 1. So that's 1 over, I could say 1/2 x minus 1/2. And that is nice and pretty in slope-intercept form. And I can see the slope is 1/2, the y-intercept is -1/2. Okay, you could compare that to what we graphed. Did this have a y-intercept, it looks like, at -1/2? Okay, and if you count between these points, the slope is rise 1, run 2. So yeah, it had a slope of 1/2. So it had a slope of 1/2 and a y-intercept of -1/2. So that matches the graph that we created, right? You'll feel okay with inverse? From a table and graph and from an equation. So I'm going to do one example, putting it all together, and then y'all are going to try one with your group. Okay, so flip it over. I'm going to go ahead and save us some time and tell you, instead of pulling up Desmos and showing you what it comes up as, I'm just going to fill in our table for us and tell you what it is. So it comes out, what is that? 1/2 x minus 3. So I want my table to be at -4. That'll be -5 for the y value. At -2, that will be -4. 0, -3. And then we want 2 and 4. So at 2, it'll be -2. And at 4, it'll be -1. Okay, you could individually plug these x values into your equation and calculate that if you wanted, or you could just use Desmos. I can now plot these points and draw my line, or I could just use the slope and the intercept like I did last time. Okay, before I even graph it though, can you tell me the domain and range without seeing the graph? It's a line, right? So it's all real numbers. Now you can write it the way we wrote on the front, or we can use our all real number symbol. That means everything. Negative infinity to positive infinity is all real numbers. Oops, too big. Okay, now I can graph this by plotting the points or by knowing slope intercept form, I said. So my intercept here is -3. So I'm going to plot a point at -3, which that's on the table right here. That's your y-intercept. Okay, and then I'm just going to count my slope from there. Or you can read the coordinates and plot them. That's up to you. That's personal preference. But I'm just going to count my slope, rise 1, run 2. Rise 1, run 2. So I'm going to plot a bunch of points, rise 1, run 2, or in reverse, that's down 1, left 2. And then I'm going to draw a line through all those points. And I'm going to label this function. This is my f of x that I'm starting with. If you would like to put the y equals x line on here like we did on the front, you can, so that it gives you a good visual so you can confirm that you've graphed correctly, because you can see, oh yeah, that reflects over that line. Okay, so if I could graph this without the table, I don't have to fill in the table. I can just individually look at these points and say, okay, this point is on that line, so it's going to stay the same. Okay, this point on the gray line is at -4, -5. So what is that if I flip it? Instead of -4, -5, I'm going to go -5, -4. So I'm going to put it here. And you could individually just pick out points here and switch the x and y and plot them. Now, for most of us, though, it's nice to just rewrite the table. See, what was in the y column or f of x column is now in my x column for the inverse. And what was in the x column is now in the y column. Okay, and I can plot all these points. I already got the -5, -4. So I need -4, -2, -3, 0, -2, 2, and -1, 4. So I could keep going. Can't I just count the slope between these peak points and figure out what it is and keep repeating it? What is the slope between the pink points? What's my rise over run between these? Rise 2 and run. So I could just keep going up 2 over 1, up 2 over 1, up 2 over 1, or down 2 left 1, down 2 left 1, and then draw that line through those. And I'm going to label that one as the inverse. And I didn't label this. I'm going to label this y equals x. Now, while I'm on this graph, I identified the slope. Did we just plot the y-intercept of that inverse right here? Right there? What is that y-intercept? That's at 6, so that's my b, isn't it? So if I'm asked for the equation of the inverse, and on my graph, I can see the y-intercept, and I can count the slope, can't I just write my inverse function as mx plus b? Y'all see that? Mm-hmm. So I can use the graph to write my function of the inverse, or I can do the 4-step process using the algebraic steps. Yep. Is that? Yes, sorry, that's a b. Like my y-intercept b is 6. All right, now I'm still going to show you for the sake of your notes, because they ask us to actually do the algebra. So I'm going to go through that 4-step process and replace f of x with y. I'm going to switch x and y. And then I'm going to solve for y. How am I going to solve this for y? What moves first? The -3 by addition. So this becomes x plus 3. Now, I've got a 1/2 multiplied by a y. How can I get rid of that 1/2? I can divide by a fraction. I can divide by 1/2, but what's an alternate? Because I don't like it to be messy. Dividing by fractions can get messy. I could do decimals instead, but instead of dividing at all, instead of having to deal with dividing by a fraction or a decimal, who remembers what you could do instead? Multiply by what? No, because if I multiply by 1/2, it won't reduce, it won't cancel. 1/2 times 1/2 is 1/4. It wouldn't get rid of it. It would just change it. What would get rid of that 1/2? What could I multiply by? 2. Okay, so remember, I'm going to put 2 over 1 so you can see it. It's when you take the fraction and you flip it upside down, then everything will reduce, right? And you're left with just the y. So that's called the reciprocal. If you forgot, you can multiply by the reciprocal instead of dividing by a fraction. Now, what you do to one side, you have to do to the entire other side. So notice I'm putting parentheses around it, and I'm going to multiply by 2. So that 2 is going to have to be distributed there. So I get 2x plus 6 for my inverse. Isn't that what I got from looking at the graph too? So you can get it the same way. Okay, so my equation is f inverse of x equals 2x plus 6. I showed you how to get it from the graph and doing the algebraic process. If you want to make a note here that I multiplied by the reciprocal. I don't know if I spelled that right, but whatever. Multiply by the reciprocal instead of dividing by a fraction. You could make a note. That's what we did. So you remember you can do that. You can multiply by the reciprocal instead of dividing by a fraction. You'll feel okay about that? Oh, domain and range. We could have answered that at the very beginning without even knowing the equation. What's the domain and range of the pink line? Yeah, it's all real numbers also. negative infinity to positive infinity. It's a line. All linear functions have a domain of all real numbers and an inverse, or excuse me, a range of all real numbers. Okay, so I'm going to give you a minute or two to try number 2 with your group. Okay, I want everybody to try it, talk to each other if you get stuck on something. Okay, give number 2 a try and then we'll check it. When you finish that, if you're finished before we check it, you can log into Delta Math and start our practice that we do have a little practice assignment over inverse linear functions. Okay, so there's a Delta Math, but try example 2 here at the bottom of the notes, and then we'll check it. Okay, I'm recording this, so I'm going to freeze y'all's screen here in class. For those of you watching the video, just pause and try it. I'm going to go ahead and scroll up. So pause before you see the answer. This is the one you're trying. And then here is, I have the solution open somewhere. I already saved it in this folder. Oh no, here it is. Here's the solution. So what you, if you tried it, this is what you should have gotten. Okay, and I'm going to go ahead and end the recording here. Just try Delta Math.